Well, I'd like to welcome Adam Kaplan to stage 2 this afternoon. And Adam is going to take us through a presentation on 3D propeller inspection. Over to you, Adam.
Thank you. Yes, appreciate that. Hello, everyone. Thank you for watching or tuning in. Today, I'll be talking about how shipyards, boat builders, and dry dock operations can leverage new technology to assess the condition of a propeller, and this can be done, directly in the shipyard. I think everyone intuitively knows that the propeller is a major influence in ship performance. Top speed, bollard pull, engine load, fuel efficiency, cruising RPMs, these are all driven by the torque and thrust, the torque demand and the thrust produced by the propeller. Intuition also tells us that a geometrically precise and well matched propeller will outperform a damaged propeller or an otherwise non optimal propeller. And, propellers are one of the most critical components of a vessel's performance system or propulsion system. And their condition directly affects fuel consumption, speed, vibration, and even drivetrain reliability. So in dry docks, shipyards are under constant pressure to complete inspections quickly, control labor costs, provide accurate documentation for the owners and the class societies. Now, traditionally, propeller inspection has relied on manual gauging, templates, visual surveys. And these methods are really very time consuming. They're subjective sometimes. And often they only provide partial geometric information about the propeller. So today, full 3D scanning allows us to digitally capture the entire propeller geometry directly in the dry dock. We don't have to remove the propeller. And this allows us to create a precise digital model that can be used for inspection, reporting, and even further engineering analysis. The key benefit for shipyards and people managing shipyards is the time and cost reduction. Many yards traditionally remove the propeller from the vessel and they outsource the work to a dedicated repair shop. And removing the propeller, that requires a crew, scaffolding, cranes, rigging, transport, and all the associated costs with that. And so a slightly better solution is to outsource that work to maybe a mobile propeller service to perform that work in the yard. But nearly all shops use some form of manual measurements. So by utilizing full 3D scanning tools, there's a major opportunity for significant savings. Now, so first, dry dock time is expensive. Rapid in situ scanning can reduce inspection time from days to hours, freeing dock space sooner and improving the yard's throughput. And so second, labor costs drop significantly. Instead of large crews taking manual measurements at multiple stations on the propeller, a small scanning team can completely capture the geometry in a single workflow. And that reduces scaffolding, rework, repeat inspections due to missing data, things like that. We capture a full model of the propeller so that we don't have to go back. Third, the output is actionable engineering data. We can quantify blade deformation, thickness loss and erosion, pitch deviations, and really quantify the severity of the damage on the blades. And this helps shipyards plan repairs, validate tolerances, and demonstrate compliance. Now, finally, the 3D model, it becomes a permanent digital record. And where the life cycle of a ship may be up to 50 years, and it may go through multiple engines, multiple propellers. having a full 3D digital model is really important. It supports QA documentation, owner reporting, life cycle monitoring. It allows you to look at future performance optimization. So really the conclusion here is that 3D propeller inspection transforms dry dock surveys from a manual check into a data-driven engineering process that really saves time, it reduces cost, and it improves technical outcomes. So let's look at what this means in practice. In a typical dry dock, a full propeller inspection using manual templates and gauges, that can take 1 to 3 days, depending on the size of the prop and the access. And if you had sent it out, paid for the rigging, the transport to a specialist, you're waiting on their schedule, and then they can turn around and send it back to you. That might be a 1 to 2 week turnaround time. So with modern 3D scanning workflow, that same inspection can be completed in a few hours. So now labor, let's look at the labor differences. This is another major factor. Manual surveys, they often require multiple technicians, scaffolding, repeated access to the prop. And with 3D scanning, we could do that with a small team, usually just 1 or 2 people. Recently, we did a 110-inch prop with 2 people, and it took 4 hours to do 2 props. So that allowed us to capture the entire geometry, both sides of the propeller also, which aren't traditionally inspected. A lot of times they're focused on the pressure face. So now we're getting a full 3D of both sides. And that kind of brings us over to measurement coverage. This is where the real technical shift happens. Traditional methods, they measure discrete points and sections. Now the 3D captures the entire blade surface, every square millimeter, allowing us to detect subtle deformation, erosion, and manufacturing deviations. The accuracy and the repeatability, they're significantly improved. Depending on the scanner, we can actually achieve sub-millimeter resolution. And it's a non-contact process. There's no deflection in the template or the drop rod that's probing physically on the surface. So the results are super repeatable, digitally traceable. And the output is not just an inspection report, but it's a full digital twin that can be used for repair planning, documentation, and long-term performance tracking across docking cycles. So all of this enhances the outcomes for the shipyard, and it provides numerous benefits that can instantly give you a return on your investment. So now let's talk about propeller quality. Any propeller that you inspect, even a new propeller, will have some geometric variance between the blades. Now, whether this variation was from the manufacturing operation, delivery, installation, striking something during operation, we know that variation will have some effect on the prop's performance. So we'll just refer to the variations as damage now, just for getting through. It may not be damage, it may have been born that way, right? So damage to even a single blade, it changes the loading on the blade, which leads to more losses, more imbalances, and that directly impacts the efficiency of the propeller. So that's less thrust and higher power requirements, and that's going to reduce operating speed, higher fuel bills, more noise, and more vibration. And if left unrepaired, that can really damage the bearings, gearboxes, and other things upstream. And that's due to those eccentric forces and imbalances. So, these propeller issues are common, and not all of the damage is obvious from a visual survey. And that's why regular inspection of the propeller is so important. And again, if you are struggling to fit propeller inspection into your dry dock schedule, this is a way to accelerate those timeframes and get even better data out that covers that for you. So when we're inspecting a propeller, we are checking the geometry of each blade to minimize that variation between the blades. Um, it's that variation that really alters that relationship between speed and RPM and engine load, and differences between blades or damage to blades. Sorry about that. Gotta go back there. That leads to reduced top speed, increased fuel use, all that stuff. When we inspect a propeller, even with gauges or manual measurements, we are taking pitch measurements for each blade of the propeller. And we a lot of times we'll visualize these with bar graphs where there's a tolerance and there's a window of acceptability. And then we're plotting each blade against that. And we break this down by blade, by radius line, and we even break them into smaller segments. Sorry about that. That measured pitch can vary from the target pitch by some specified amount. So it's really important that we're checking to make sure that all of our measurements are within this window. So whether you're doing it manually or with 3D scanning, this is kind of the objective, is to check those and balance those out. So how do we know how much variation is going to be acceptable? Professional repair facilities use a standard called ISO 484. That's a manufacturing tolerance for marine propellers. And this standard has long been the metric for inspecting both commercial and recreational ship propellers. There's 4 classes to document the condition. S is the tightest class level, 1, 2, and 3, with 3 going to the widest tolerances. And those inspection methods, they're outlined in ISO 484, and that's what's used to calculate the geometry for each blade. This is the standard that we use for compliance. So, what our team does and what our software does is basically allow us to go from the 3D model or the inspection data to the documented report. And that's really the end goal of this, is to document compliance, right? So let's look again at kind of how this process works. We're leveraging commercial metrology equipment. Typically, this is handheld blue light laser scanners. And that gives us a new way to inspect the propeller, again, without having to send it away to a specialist, without having to remove it from the ship or pay for rigging and transport. So in scenarios like maintenance and dry docking, that's a super valuable thing. Again, it accelerates the timeline and it reduces cost. And there's lots of options for 3D scanners today. They are very accurate and they're as good. Typically, they're much better than the traditional probe-based measurement tools or the gauging and the template option. And one advantage is if you scan the propeller and it's in good condition and you haven't removed it from the ship, you're bypassing a lot of unneeded labor for the removal and for the rigging. Here's another example. We can see a large propeller being scanned. I want to point out that this technology can be used for propellers as small as 8 inches and as large as 160 inches, which makes it super versatile. It's great for controllable pitch propeller blades. It's great for high blade area blades with overlap because you can move that scanner in between the blades. And, our TrueProp software, our solution, that supplements this and makes it really useful. It takes that 3D data that's captured and it extracts the data needed to check those tolerances across the blade. It produces a report that documents not only the 3D shape of the blade, but it's actually giving you the tolerances across the blade. And it shows you any areas that are out of spec for that desired class rating, that S1, 2, 3, 4. So this software really, it's compatible with anything that outputs an STL mesh, and that includes older, metrology arms with laser scanners that some machine shops might already have use. So you don't need a handheld laser. You can really use anything that makes a digital model, which makes this extra flexible. Here's another large propeller being scanned. I'm not sure what size this is, but this is, I believe, a Coast Guard wheel. And just another interesting process. You can see how fast he is going through scanning that prop. No other specialized equipment really needed beyond the scanner that he has in his hand, the laptop here. And you can see that there's a second operator in there who's kind of helping him. He's watching the laptop, making sure all these areas are captured. So again, 1 to 2 operators, and that would cover you up to 140 inches, 160 inches. I don't see any reason why you would need more than 2. So that's a huge advantage, right, on labor. And I wanted to show you a few more images here of different scanning processes. We can see a large propeller being scanned. You can see in the hub region here, there's some overlap between the blades, and it's also very, very steep, which would be a little bit troublesome for our typical drop rod based approach. So by going to the 3D scanner, no issue at all. And the other example I'm showing here is a CPP blade. So we can inspect these CPP blades without any sort of fixture or original hub or a dummy hub that would traditionally be used. We can just orient the scan model in CAD and analyze it. It's a really, really cool strategy. Scanning the propeller into a 3D model alone, that's kind of the first step. But to make really good use of it, you need another layer to extract and interpret the necessary data. That's just what our software does for these types of models. Here's a couple examples of the screens there. We can see that we get a 3D model. We are mimicking the traditional process here with scribe lines at set locations like they would do with a template. But we're doing it all digitally, so it's very quick. It's easy to revise. We are getting the lines that show us the shape of the propeller, and then we're actually showing areas that do not meet compliance on the leading edge of this blade here out at the tip. So this particular surface piercing propeller had some issues. If we zoom in down here at the bottom, we can also see some regions that are out of compliance right here. You can see that they're exceeding those tolerance windows. And that's why we're looking and noticing damage and quantifying that, identifying it and documenting it. Just another example here. This was a large propeller that was inside, I believe it's a tunnel thruster. And so access to this was pretty difficult. It was inside of a tube, basically. But 3D scanning allowed us to capture that geometry without having to remove it. And we were able to extract data right out of it. Pretty basic design, some pretty tight tolerances. Nothing wrong with this prop, so it was good that we didn't remove it. This propeller here, I believe it's 123 inches. So it was a very big propeller and would have cost a lot to remove. Again, more examples here. Actually, I think we've seen all these already, so I'll just skip through this slide. Now, it's great that we can capture that geometry. What else can we do with that data? There are lots of post-processing tools to digest that data. It's really just a surface mesh model or a cloud of points randomly positioned in space. So that doesn't alone tell us anything about the geometry or the condition. We can maybe calculate some areas, volumes, and weights, but we want to know pitch, diameter, thickness, and things like that. So, depending on what your objectives are, from the 3D model alone, if you have something to compare it to, maybe another scan or a CAD design model, you can quickly get a heat map. That's a really useful visual, very compelling. It tells a good story, right? But, that doesn't tell you anything about the condition. So we would use TrueProp here to basically check the propeller against its design specs and analyze the tolerances, determine the class. We would also use a product from HydroComp for, more or less recreating blade geometry, creating a drawing from a blade to supplement missing documentation, or to create a new blade for manufacturing, to get a new pattern made, a new propeller made based on the scan data we pulled. So there's a lot of things that you can do with that so-called digital twin model. And just a little bit here, this is the tail end of it. Just a little bit about TrueProp. We started in 2017. We create software tools and integrated machines to inspect propellers. And our goal is to provide customers with the highest quality analysis, repair guidance, and compliance reports so that they can then provide ship owners and operators with the best performing propellers possible. And traditional propeller inspection, it's been performed by propeller specialists who have the equipment to handle, measure, and refurbish props. And that really is our primary market. But more and more, we are seeing shipyards, dry docks, and ship management companies adopt this software, adopt these technical tools so that they can also play a part in this and benefit from the cost savings and the accelerated schedules that are possible with it. And then another just following note on HydroComp, they're a sister company to us. They have a lot of propeller specific tools for both CAD geometry and performance. So if you're looking to do more detailed engineering, that is a good product to review. And I'm going to skip through these as I believe we're out of time, and I'll just go right to closing slide here. Great.
Okay.
Yeah.
Thank you. Well, we do have a question. So we've got a question here that says, how do you calculate the pitch at a certain radii?
Sure. Yeah. Essentially, it comes down to a geometric formula. Really, it's about the angular span, across one of these lines. Let me see if I can get to a good slide here. So we have these lines up here. We're looking in cylindrical lines. So what we need to do to calculate pitch, we're identifying an angular span and we're identifying a drop. And it's essentially a ratio between those two. The formula itself is a little more complicated, but those are the two measurements you really need is the angle and the drop. And that's really what we're extracting out of the 3D model.
Okay, thank you. And then a supplementary, which I think I'll interpret correctly, but is it possible that there might be no scanned points along the radii?
Well, I would say it depends on your scanner. So we have the ability to select the spacing between the points on most 3D scanners today. So, and the density is usually 1/10 of a millimeter by default. So, we can up that to a millimeter. We can up that to 5 or 10 millimeters, depending on the size of the prop. What will happen is if the points are not directly on the radius line, when we make a mesh out of the point cloud, it will interpolate over that.
Yeah.
So we'll essentially have a small panel there instead of a single point, and then we can pull an intersection from it. So it's a very accurate method and pretty standard for CAD programs to do that type of interpolation. So as long as your point spacing isn't too high, you'll have no problem at all.
Very good. Well, Adam, thank you very much. It sounds a very interesting technology. and thank you for your presentation.
Absolutely. I appreciate the opportunity to present, and I hope some people come away with something new that they can maybe implement in the future.
Very good. Thank you.
Thank you.